Good morning, everyone. Today we'll do experiment number 5 to find the order, cutoff frequency, and poles of the digital Butterworth filter using impulse invariant method. Okay, so this is specifications. Okay, so this is your K1, this is your K2, and these are your omega P, and this is your omega S. Okay, um, you notice that your K1 and K2 are not in dB. Okay, so you have to convert them to dB using this formula. And your omega P and omega S is already in radian per second. So we leave it as it is, which is divided by the value T. Okay, since we're going to do it in the since we're designing a digital filter. So we got this value. Okay, match it up with your Matlab programs. Okay, so from the previous class I've taught you how to find the order and the cutoff frequency. I'm not going to do it again, so please refer the previous videos for that. So since the order is n is equal to 2, this is a standard Butterworth filter formula for it, for order n is equal to 2. So in step number 2, what I'm going to do is instead of s, I'll just substitute it with omega c values. So here instead of s, wherever s is there, I'm just dividing it by omega c values. Okay, I think by mistake here it should be square. Okay, because here s square is there, so this value also should be squared. Wherever s is there, I'm dividing it by the cutoff frequency. Kindly solve it. So your final equation should be something like this. Okay, matched up. So the other one is next step 3 is to find the poles of your analog filter. To find the poles is you just have to use that formula b is equal to s is equal to minus b plus minus root of b square minus 4ac divided by 2a. Just use that, you'll get these pole values. And in step 4, you have to find the partial fraction of your analog filter. You have to find the thing of your analog filter. So here using partial fractions, I guess you know how to use partial fractions. I'm not going to teach you in this class. Please refer any other videos for it. So my HA of S is equal to this much, which is equal because there are two poles. So I'm going to divide into A and B. Okay, this is a plus sign. It's not so prominent. So because there are two poles, I'm dividing to A and B. So my A value, I'll get this much, and B value is this much. So I substituted back into the original HA of S. So I'll get instead of my A value, I'll get this much, and my B value will get this much. So after partial fraction, my HA of S filter will look like, HA of S transfer function will look like this. In step number 5, so because we have to find a digital filter using impulse invariant method, till now it's still in the S domain, means it's still in the analog form. We're going to convert it to the digital form using this method. So in this method, what actually is, this is actually K, this is actually pk, this is subscript pk, by the way. Okay, so where k varies is equal to, where k varies from 1 to till the order n. So this is also k. While changing the format from PDF to from doc to PDF, it got changed. So okay, so in this formula what it says is when if c of k, this is in the analog form, it should be in this form of cks minus pk. It will be transformed into digital signal using ck 1 minus e to raise to the power pkt z inverse. So I did just that instead of pk. So this is already in the form of, so if you see this is already pk, and this is ck. So actually this is c1, this is p1. Okay, so this is p2 and this is c2. Okay, because the order is 2, so you're going k is equal to 1 and 2 only. I've substituted here. So this is my poles pk, this is p1. I've just put it here. Please keep it in mind, this is s plus, so your poles is opposite values to that. opposite sign to that. So this is my P1 values. Okay, my CK, my C1 and C2, they are almost same values, so I've taken them out and we've just put the minus sign and the plus 1 here. So solve it, kindly solve it, so you'll get a generalized digital filter of this form. Okay, so if you can find the poles for this also, using h of z is equal to, sorry, this should be like this, h of z is equal to like this. So this is a transfer function in one form and this is in another form. So done with your calculations. So in the Matlab, how you enter is similarly clear. I think by now you know all what of this is all about. So this is omega p, omega s, k1, k2, okay, with 1. So this is k1, you have to change it into dB form. So you have to multiply it by 20 log. And this is because we're using impulse invariant method, we just dividing it by the sampling frequency. So n is omega c is equal to Butterworth. Since we're trying to do an analog format, so we're using s. So this is just to find out the standard equation, how it looks like. So this is literally step number 2. Till here it is step number 1. Till that's step number 2. This is finding HA of s. So this is HA of s is step number 3. Just check it out. HA of s is okay, and then this whole step is step number 4, 5 and 6. Okay, so that's it. So you kindly check the kindly check your output and see how it's displaying. Similarly, after solving all, that's it for the previous problem. This one you do it as an assignment and submit along with your report. Design a Butterworth filter for the following specifications. Remember, this is already in radian per second, so you need not change it, and this is already in dB, so you need not change it. Keep that in mind. Again, simple sampling frequency of 1 hertz using impulse invariant method. That's it for today's, guys. Please submit your assignments on time. Thank you.